Hello, everybody. It's Dr. Hannick. So anyway, I'm going to be continuing here with the refractory periods. Um, so the refractory period is a time in which the neurons cannot be triggered by another action potential. And the voltage gate sodium channels are still open, so a neuron cannot respond to another stimulus while these voltage gated sodium channels are still open. So we have two types of refractory periods. The first one is absolute refractory period, and this is the time from opening of sodium channels until the resetting of these sodium channels. And the purpose of it is it ensures that each action potential is an all or none event. So every successive action potential following it will have the same exact uh, parameters and stimuli and so forth. It enforces also a one-way transmission of the nerve impulse. The relative refractory period, this follows the absolute refractory period. Most of the sodium channels have returned to their resting state. Some potassium channels are still open. Repolarization is occurring, so we're reestablishing the resting membrane potential. And a threshold to generate an action potential is elevated during this refractory period. And so therefore, if you want to cause another action potential during this relative refractory period, an exceptionally strong stimulus would have to be generated in order for that to happen. So here is the picture showing you the graphic representation. The green represents the absolute refractory period, and the blue, the darker shaded blue here, represents the relative refractory period, where for the most part, repolarization is occurring, hyperpolarization, and then establishing the new resting membrane potential. So during this relative refractory period, if a very strong stimulus that exceeds this higher threshold is achieved, you can generate another action potential. However, during the absolute refractory period, during this time, regardless of the stimulus, no action potential will be generated again. So the conduction velocity, so the speed at which these action potentials will occur is based on these factors. The first one is the diameter of the axon. So the larger the diameter of the axon, the faster the action potential will occur because there's less resistance. The second one is the degree of myelination. And the non-myelinated structures, the action potential moves slow and continuous, but the myelinated axons, that's saltatory conduction, and that moves significantly faster, up to 30 times faster than the non-myelinated. So here we could see basically what I've just said as far as this is concerned. So I'm going to show you just the visual here. So here in bare plasma membranes, voltage decays. So here at a particular dendrite here, here's the stimulus that was occurred, and the size of the voltage, as you can see, significantly decreases as we move away from the stimulus. And as voltage decreases, the conduction of this also is associated with a slower movement. So, and these are usually very short segments, short distances, and they move slowly. The next one is in the axons that are non-myelinated. Their conduction is slow, but they're continuous conduction. And here, once again, you have this repolarization occurring as we move away from the stimulus. But these little voltage-gated ions kind of recharge the voltage so that it kind of speeds up. But the process of these voltage-gated ion channels are slow. So the propagation of this impulse moves slow because of this, because of the delay, the time it takes for it to occur. Next, myelinated axons. Conduction is very fast. Saltatory conduction. The myelin keeps the current in the axon, so it insulates. So as you can see, the dissipation or the decrease in the voltage in this case is more gradual. So as we said, if you increase voltage, the current will also increase in terms of the speed. So we have it here, and in this case, this myelin sheath gap, which is called the nodes of Ranvier. Here we have these voltage-gated ion gaps that are very fast, that supercharge and recharge the voltage, so it causes this to continue very fast with very little resistance, and the flow is extremely quick. So pathology. MS, multiple sclerosis. In this case, it's an autoimmune disease, so the body produces antibodies that attack and destroy the myelin sheath that surrounds the axons. And it turns the myelin into these hardened lesions called sclerosis. As a result of that, the impulse conduction slows and can eventually even cease. And demyelinated axons increase sodium channels, causing this cycles of relapse and remissions. So as a result of this, symptoms, visual disturbances, weakness, loss of muscle control, speech disturbances, incontinence, the strength of the muscle also will decrease because impulses that normally would reach their effector organs are blocked because of the lack of myelination. Some of them become that inactivated, or the impulse is blocked. Treatments, drug that modify immune system activity, and it may not be able to prevent it, but maintaining high blood levels of vitamin D may reduce the risk of further development of MS. Now, conduction velocity. Nerve fibers are classified according to their diameter, the degree of myelination, and speed of conduction. So they fall into three groups. So group A fibers, these are the largest diameter, very little resistance. They are myelinated, somatic, sensory, and motor fibers of the skin, skeletal muscles, and joints. Their transmission velocity is 150 meters per second, or roughly 300 miles per hour. So as you can see, how fast you respond to different stimuli or commands, and it's because of these group A fibers. Group B and C, in this case, the diameter starts to decrease, the myelinated fibers become less myelinated, and as a result, you can see that the transmission velocities significantly decreases. So here, down to 30 miles per hour in group B, and in group C fibers, which are the smallest diameter axons, unmyelinated, they are at like 1 meter per second, or about 2 miles an hour. Both B and C groups include the autonomic nervous system, visceral motor, and sensory fibers that serve the internal organs. We don't have organs that move very quickly or respond very, very quickly. They are slow. So it's not surprising we have the cardiac and smooth muscle are slow compared to skeletal, which is slow to very fast. Impaired action potentials, impulse propagation can be caused by a number of chemical and physical factors. Local anesthetics block the voltage gate sodium channels. Colder temperatures or continuous pressure interrupt blood circulation and delivery of oxygen to the neurons. And, so cold fingers get numb or foot goes to sleep. This is the end of this first segment of video. Thank you.